So hopefully we have a good understanding of what position, distance, and displacement are. So now I'm going to introduce you to two new quantities. So the first one I'm going to introduce you to is speed. Now we've all heard speed before, then the most common place that we've probably heard it is, in our car. So because a car has what's in it known as a speedometer, which, guess what, comes from the word speed. So these are in miles per hour generally, and we'll explain. I'll go a little bit more in detail what miles per hour means. For now, let's say our speedometer is pointing to this 40. That means that our speed right now is 40 miles per hour, and we say mph, but what mph really means 40 miles per hour. And we can think of speed also in speed is a scalar, because if we're driving in our car and we're going north, the speedometer points to 40. If we're in our car and we're driving east, the speedometer points to 40. The speedometer doesn't care what direction you're driving, as long as all it cares about what is the magnitude of your speed, or how fast are you going. So speed is a scalar. And we can relate speed, we can relate average speed, and we can think about a little bit about why we say average speed instead of just speed, especially when we go into more calculus. But for now, you'll have to trust me when I say that the average speed is going to be equal to the total distance divided by the total time that's elapsed during our driving. So, and it makes sense that speed is a scalar because we know distance is a scalar, and we know we haven't really talked about time. So people can make the argument that time is a vector because it has a direction. You can say I'm going forward in time, or in sci-fi movies they say I'm going backwards in time. But for the purposes of especially classical physics and classical mechanics, we treat time as a scalar because you can't really treat it it doesn't really have directions in the same sense that the other vectors do. You can't say I'm going northward in time, I'm going east in time, or west that doesn't make any sense. If you told someone you're going south in time, they would look at you like you were crazy. So for our purposes, we're going to say time is a scalar. So it makes sense that a scalar divided by a scalar gives you another scalar. So now let's talk about the vector version of speed, which is called velocity. You've probably heard velocity before, and maybe you weren't too sure what the difference between speed and velocity is, and so now hopefully we'll illustrate that difference. Velocity is the same in speed in the sense that if I'm going 40 miles per hour, the magnitude of my velocity is 40 miles per hour. But velocity also, being a vector, it has a directional component. So if I were to say I'm traveling at 40 miles per hour, that is still that's just a speed. But if I were to say I'm traveling 40 miles per hour to the east, that I now have a direction, and I now have a velocity vector, because the difference between, again, vector and a scalar is that a vector has a direction. So we can say that the average velocity, and I'm gonna introduce a new symbol here, and that's the symbol for average. So v, which is velocity, with a little flat line over it. Let's make that a little bit better. V with a little flat line over it means average velocity, and that's going to be equal to the displacement divided by the time. And again, this makes sense. We have displacement is a vector, and time is a scalar, so it makes sense that a vector divided by a scalar will yield us another vector. So let's consider the racetrack again, and this time I promise to try and draw it more neatly. This time we'll say that it's 400 meters in length. So let's say Bob runs one lap in 1 minute, which is a pretty fast time. I can't do that. But anyway, so Bob runs one lap, which is 400 meters, in 1 minute, which is 60 seconds. and I want to know what is his speed and what is his average speed and what is his average velocity. So his average velocity, and maybe it should start making sense why we keep saying average, especially if you've done work in calculus, and you'll certainly understand as we actually get into calculus in these videos. So the average speed is going to be distance over time. And when I say time, I don't mean all of time in its ever-expanding relative expanse. I mean the change in time. Because I don't care that, that the universe has existed for billions and billions of years. I only care that about the 1 minute the 1 minute it takes for Bob to run around the lap. So what I really mean by distance over time, I mean distance that he runs divided by the change in time. And so now from now on, we'll be thinking of things in terms of change in. And so in order to keep us from, constantly writing change in, we use the Greek letter delta to denote change in. So we can say that the distance d divided by the change in time, and we can say the capital Greek letter delta. So this literally translates in English to change in time, which we abbreviate with t. So now let's do that. So if average speed is distance, which is 400 meters, and divided by the change in time, which is 60 seconds, because typically we'll give stuff in meters per second, which is seconds is the SI unit for time, and meters is the SI unit for distance and displacement. So 400 divided by 60 is 40 over 6 is 20 over 3 meters per second, which is 6 2/3 meters per second. So that means that for every second that elapses, Bob runs 6 2/3 meters, and that's pretty fast. So now let's think about his average velocity, and maybe if you remember the last track problem, you might already know the answer, but we'll go over it anyway. So we remember that average velocity, which we know is this v with a little line over it, is going to be equal to, well, you know what? We can say change in displacement because change in position, which is the definition of displacement. So change in position, and again, I'm introducing the change in, divided by change in time. And we can write this in a more compact way by saying, again, capital Greek letter delta s, which is our unit for position and displacement, divided by capital Greek letter delta time. So our average velocity is going to be equal to delta s over delta t. And so if I say delta s, I mean literally change in s, or change in position, because that's what delta translates to. So what is our displacement for this guy running the track? Well, if he ends up remember that change is a vector and it's net position. It's the net change in position. So if he starts the race here, he runs around the track, and he ends up where he started. So again, his displacement, if you remember from when we did the last sample problem, is 0. And his time is still 60 seconds, so we'll say 0 meters divided by 60 seconds. And this translates to 0, because 0 over anything is 0. Well, everything for 0 over 0, but don't worry about that. So we had 0 meters per second. And again, we know that velocity is a vector, so there is a direction encompassed in this, but it's kind of hard to imagine a direction if you're not going anywhere. So you'll have to bear with me that I can't really give this a direction. But had there been a positive velocity, then we would have a direction. So this is a couple sample problems, and just to get you hopefully introduce the idea of velocity and speed. And until next time.